Good morning, students. Now, in this video, we are going to discuss brief about the chemical composition analysis. Chemical composition of a powder is an important factor because it influences further processing such as compaction, case of ejection, as well as the degree of densification. See, many chemical reactions are possible within the compact. See, we mix all the powders, we compact that powders. Okay, so after that, we apply the pressure on the powder mixture in the die, and then we sintered that powder in the sintering atmosphere. Okay, chemical composition, it determines the sintering temperature, type of sintering, and the atmosphere to be used, as well as the properties of titanium sintered material. Chemical analysis, in addition to the elements present, must also give the amount of metallic and non-metallic impurities. See, when we mix the powder, there may be metallic impurities and non-metallic impurities. The impurities can be in elemental form, or chemical composition of the powders can be analyzed by chemical methods. Chemical analysis shows the estimation of gaseous impurities like oxygen, hydrogen, sulfur, impurities like carbon, and other insoluble materials like silicates. See, when we mix the powder, so in that powder there may be the gaseous impurities, as I told. The techniques to analyze the different forms of impurities are different. For example, the technique used to detect silicon may not be suitable for accurate if the silicon is present in the form of compound silica rather than in solid solution. If the element present in the solid solution, then it may be sometimes undergo chemical reactions during the sintering. See, when we carry out the sintering process, then at that time that element may undergo the different chemical reaction. Chemical analysis. Oxygen content of the powder is measured by hydrogen loss method. The value of oxygen loss gives an appropriate estimate of the oxygen content of the powder, which is an essential variable. Now just see here, one chart is given here. See, in the first column method, in the second column particle and remarks. Wet chemical analysis, dissolving the sample and using various techniques like titration, spectroscopy. Inertness problem, detection up to ppm levels possible. X-ray fluorescence, it records characteristics of X-ray lines. Non-destructive calibration necessary, detection up to ppm levels possible, surface sensitive. Then emission spectroscopy, vaporization of the sample and recording the optical spectra, detection up to ppm levels possible. Neutron activation analysis, irradiating the sample and recording the radioactivity. It is expensive method. Then energy dispersive X-ray analysis, EBXA, measuring the energy of X-ray lines. It is a qualitative, flat surface required, light element problem, non-destructive. Then electron probe microanalysis, measurement of wavelength of X-ray lines. We measure the wavelength of the X-ray lines. It is quantitative, flat surface required, light element detection is a problem. X-ray diffraction, measurement of diffraction angles and comparison with JCPDS files, rapid qualitative. Particle shape, See, the particle shape depends on the method of powder manufacture. First point. The various shapes are spherical, rounded, angular, dendrite, porous, and irregular, etc. The particle shape influences the flow characteristics of powders. The particle shape and effect of packing of a powder and has an influence on its compacting and sintering properties and the mechanical strength of the sintered product. The irregularity shaped particles have reduced apparent density and flow rate, but good pressure and sintering properties, whereas the spherical particles have maximum apparent density and rate, but reduced pressing properties and good sintering properties. Powders too have reduced apparent density and poor flow rates. Now see here, one table is shown here. In the first column, dimensionality. In the second column, shape is considered. In the third column, representation. And in the fourth last column, example is considered. One dimensional, two dimensional, and three dimensional particle size. Shape is acicular, rod like shape. Chemical decomposition and comminution. Two dimensional particle, okay, shape is dendritic, flaky, and plate like. Electrolytic, copper and iron, ball milled, okay, aluminium. Three dimensional, spherical, rounded, angular, sharp, irregular, porous. Inert gas atomization, precipitation, carbonyl process, atomization, chemical decomposition, communication, comminution, carbonyl process. Particle size. Particle size can be defined as the total space occupied by a powder particle. Okay, the particle silicon carbide has a great importance because it affects some of the important properties such as grain strength, density of the compact, as well as agglomeration, porosity, dimensional stability, etc. The metal powders results in poor apparent density, poor flow rates, and maximum sinterability, while coarse powders give good apparent density, good flow rate, and minimum sinterability. See, in the examination you have to write just point wise. Interparticle friction and flow characteristics. Friction between particles affect ability of the powder to flow rapidly and pack tightly. Okay. Second point, a common test of particle friction is the angle of repose, which is the angle formed by a pile of powders as are from a narrow funnel. You see, it is a narrow funnel. It is a funnel. Particle sizes generally show greater friction and steeper angles. Spherical shapes have the lowest interparticle friction as shape deviates from spherical friction between particles tends to increase. Thank you.